Now that we've looked at interconnection networks, let's look at the routing algorithms that send messages from one node to another. Given a current node and a destination node, the routing algorithm needs to choose the next port and channel on which to send out the message. So it chooses a port, and then the message goes over the channel connected to that port. So a routing algorithm is a function from a set of nodes and a set of nodes, in other words the source and destination nodes, to a channel. Given the source node and the destination node, we choose a particular channel. A switch usually uses one of three approaches to determine the output channel from information in the packet header. First of all, it can use arithmetic or logical operations. Secondly, it can use selecting the port based upon tables at the source. And then finally, it can use a table lookup approach where it looks up the next step to take at every point along the path. Note that multiprocessor switches need to be fast because they need to route a packet every few cycles. So let's look at an example here. Let's say we're in the upper left-hand corner of the diagram and we need to send a message to the lower right-hand corner. Well, there are several ways we can get there. We could go the step way, one step down, one step to the right, one step down, one step to the right, and eventually we get there. We could go halfway down, all the way across, and then down. Or we could go all the way across and then all the way down. Now this last path is important because it's called delta x, delta y routing. It says that we go across in the x dimension as far as we need to go, and then we go up or down in the y dimension again as far as needed. If we're in a situation where we need to go west, that is to the left, then we know that delta x must be less than 0. In other words, that the x-coordinate of our destination node must be less than the x-coordinate where we are now. If we need to go south, we know that we must be in the right column because we're doing delta x, delta y routing, and then we need to go, well, either the y node, y dimension, or the y-coordinate of the destination is less than where we are now, or it's greater than where we are now, and you can figure that out, and then north would be the reverse. And if delta x equals 0 and delta y equals 0, then we must have arrived at the last node, at the destination node, and we can send the data directly to the processor. Now, as we've seen, in this case we went in delta x direction, then the delta y direction. Usually we do routing in dimension order. First across the lowest dimension, which we call x, and then the y dimension, and then the z dimension, and so forth if we have more dimensions. So in a binary cube, the switch determines the most significant bit where the destination node number differs from the source node number and just routes the message to that node. In a hypercube, this is called E-cube routing. It was used in the N-cube hypercubes of the 1980s in the Intel Paragon, which came along a little bit later than that. Another way of doing routing is to have the source figure out where the message is supposed to go. And one way to do that is to embed a relative address in a packet header. For example, let's suppose that we have a message that starts out at 001010 and goes to 100101. So what would be the relative address embedded at the source node? Well, those two numbers, the source and destination numbers, differ in all bits but the second. So the relative address, which you get by XORing the source and destination nodes, would be 101111. In this case, again, the switch looks for the first non-zero bit and routes accordingly. More generally, you can have the source node figure out all of the steps along the way. So then it would embed which channel to take at each hop. It would embed all of those in the header. This is called source-based routing, and in this case the source node needs to be really intelligent. It needs to figure everything out. But the disadvantage is that the header is very large because it needs to contain all of the channel numbers, and also you don't know how large it's going to be, which means that your messages are of variable length. The third approach is table-driven routing, which has a small routing table at each switch. So every time you get to a particular node along the way, you look up which port you're supposed to go over if you're going to the destination where you're going. And then usually the table also contains the routing field for the next step in the route. So you're constantly stepping, and every time you make another step, you're looking up the next step along the way. The disadvantage is that all of the switches need to contain routing state, and that means fairly large tables are needed. This approach was used by ATM and HPPI switches, but not very frequently on multiprocessors, just because of the large number of routing patterns that multiprocessors need to support. You need to have, for example, adaptive routing to route around congestion, and that requires larger tables. Now, note that routing can be deterministic or adaptive. Deterministic means that given a source and given a destination, you know exactly the path that the message is going to traverse each time. If it's adaptive, that means that the path may vary based on congestion. Again, go back to our grid. Now, if we have no congestion, perhaps we'll go directly across and then directly down. But if we had congestion here, in an adaptive algorithm, we might choose to come down, go across there, and maybe more congestion, so we'll go there and then there. Routing can also be minimal or non-minimal. Minimal means no backtracking. For example, you can go here and then down and then across and then down, but you can't turn around and come back in the same direction you've gone, or you can't turn around and go up. Minimal algorithms need not be deterministic. In our first example, we saw several ways to get from the upper left to the lower right without going over any extra links. The E-cube routing took exactly as many hops as did the step function that we looked at first of all, where you go down one, across one, down one, etc. Similarly, adaptive algorithms may be minimal. Unless they do backtracking, they're not going to be any longer, the paths are not going to be any longer, just because the algorithm is adaptive. Let's compare minimal and non-minimal algorithms.